Yeah.
I have more questions.
Okay.
Good morning, Commissioners.
Morning.
I'm Ken Wilson. I'm here this morning representing Western Resource Advocates and the Southwest Energy Efficiency Project. Maybe just a couple of minutes on who I am. I received my master's degree in electrical engineering from the University of Illinois 40 years ago. That seems like a long time now. And then I spent 18 years in research and development at Bell Labs. After retiring from Bell Labs, I have had my own consulting business for the last 18 years or so. And most of that time, I've actually been involved in public policy. About 15 years ago, I was here at the Arizona Corporation Commission many times as an expert witness in telecommunications when we were dealing with the big changes in the telecom industry. And that was taking up most of the Commission's time back then, and now everything has switched to energy pretty much. And my background at Bell Labs was in large networks. The telecom network is arguably the largest network ever created. The energy grid is also a very, very large network. So I'm using what I learned at Bell Labs a long time ago when we were doing self-healing networks. We were building redundancy and reliability and self-healing into the telecom network. And what we're really doing today is trying to make the energy grid more efficient and more reliable. So it's very similar, the problems that we're dealing with now on the energy grid with those that we dealt with in the telecom network back in the 80s when we switched from an analog network to a digital network. So I'm going to try and show you a little bit today about a problem and a solution. If I can. Speak more. About 90% of homes and businesses receive more voltage than they need. This is a survey from the Department of Energy. Distribution voltages that are higher than necessary really waste energy. The average voltage, if we went over and put a voltmeter in the power outlet across and did that on an average across the country, you'd find the voltage is about 122.5 volts. And you see I've put here the desirable ranges for voltages that should be coming from the electric outlet. And there's an upper range, which is about from 120 to 126, and then a lower range from 120 down to 114. And historically, we've always seen utilities operating mostly in the upper range. And I said that high voltages or higher than necessary voltages waste energy. And that's because, if you remember, power is equal to voltage times the current, that's kilowatts. And then energy is power times time, which is kilowatt hours. So energy equals voltage times current times time. And if we lowered the voltage level just a little bit, we can save quite a bit of energy. The next question that I wanted to answer is, why do utilities run voltages high? Historically, there's been a lack of voltage measurement capabilities out in the grid. The utility doesn't have metering at most homes. If they had smart meters everywhere, they would, but historically we haven't had that. And they don't want to get calls and complaints on low voltage. So they tended to run the voltages high from the substation. Also, good metering and communication links have been expensive in the past, and that's been changing with smart grid technology. There were also, in the past, a lack of vendors that could deliver a solution to the utilities. And then I think most of all, there's been a lack of incentive for utilities to make the investments to upgrade their grids to be able to manage the voltage to a lower level. And I'll talk about how we solve that. So the solution that I'm going to talk to you a bit about this morning is called concentrating voltage or conservation voltage reduction. It's also called volt-VAR optimization in some states. It's also called distribution voltage optimization in other states. And this is not a new technology, but it is new in the way it's being piloted around the country now. It must really be done adaptively. In other words, you need the meters out in the grid, and I'll talk about that. And you need to be able to do it on an ongoing basis so that you can't just set the voltages at one level and let it go, because then you'll get into problems. So what is CDR DVO? As I mentioned a moment ago, most utilities operate in the high range of the voltage level. And they do this so that they don't have low spots on their grid that they don't know about. With CDR and the adaptive controller I'm going to talk about, you can lower that voltage level to a lower level and save energy and reduce all of the customers' energy bills. One interesting issue is what's called CDR factor. So if we reduce the voltage to the outlets by, say, 1%, how much energy savings do we get? And that depends on what the loads are and what type of equipment customers are using. It also depends on the time of year and other factors. But typically, you can almost get 1% energy reduction for every 1% of voltage reduction. And this has been seen in pilots and national standards or national studies by many people. So now I'm going to talk for a few minutes about how can the voltage ranges be reduced. First, we need to continuously monitor the feeder voltages and use capacitor banks and load tap changers to adaptively reduce the voltages on each feeder at the substation. And I have a little picture there. A load tap changer is a big transformer that can be adjusted remotely. So it has taps that can be raised and lowered, which will raise and lower the voltage on all of the feeders from that substation. The other primary element in this is capacitor banks. And if you know what you're looking for, sometimes if you're driving down the road, you can see some big equipment up on the telephone or on the power poles. And sometimes those are capacitor banks. They're used to help the power quality of the grid and to also provide voltage support. So they tend to boost up the voltage when it's low in a particular spot. Voltage regulators are used less commonly out in the grid, but sometimes you will actually need to reduce the voltage in a particular spot, and a voltage regulator is generally used for that purpose. I'm going to now walk through the steps to construct a new adaptive CVR system. And I'll just go through these briefly, and then I'll come back and show you some diagrams and how all of this works. First, you need to levelize the voltage along the length of each feeder. Typically, a feeder will have low spots. When the feeder gets long out on the end of the feeder, you may see it dropping down into the low voltage level, 114 volts or so. So we need to levelize those voltages along the length of that feeder first. Then we need to install voltage meters on each of the feeders. And that can either be in the form of meters out on the transformers or at various points on the feeders, or it could be with smart meters at the customer's location. Either one will work. We then need to install a communication system, if one doesn't exist, to get the data back to a central location so that we can do this monitoring and control. And then we need the software and control hardware that will make all of this work. And to install the CDR software to control the voltages on an ongoing, constant, continuous basis. So I'm going to walk through these one at a time and show some examples. Here I'm showing you an idealized distribution grid layout. So this kind of a Christmas tree on its side. If you're looking down on an idealized distribution grid from a substation, you have this is one feeder, and you could consider all of the little dots to be the transformers that serve 4 or 5 customers, or if it's a business or a hotel, it serves one customer. So this is a multi-branch layout. There are many different layouts for distribution grids, but I want to make it simple. We'll just look at this pretty regular grid. But the CDR will work on any kind of a distribution grid layout. The other thing that's important is the substation. And in a substation, you have transmission lines coming in at very high voltage. There's a transmission or a substation transformer that transforms the voltage down to through one or more steps to the 12 kilovolts, which is used on the distribution feeder as the main distribution voltage. What I'm showing here is a 2-step process because we do need a substation to have a load tap changer. Sometimes this additional transformer will not be stepping down the voltage as much as I'm showing here. This is just one example. In any case, you have the transmission voltage step down to the main distribution voltage of 12 kilovolts, and that goes out to all the homes and businesses where you have those smaller transformers that take it down to the 120 volt level. And I'm showing here what you might typically see if you went out and put meters at all the houses on a distribution grid. Close to the substation, you'll see higher voltages, like 125 volts. When you get out to the end of the feeder, you'll see much lower voltages typically, and those could be down in the 114, 115 volt range. So in a high load situation on a very hot day like today, when everyone's running their air conditioners, those voltages will even sink lower. And so the utility has to be very careful to maintain the voltages in an adequate range so we don't start burning out people's air conditioners or refrigerators. So the utility is very careful in what they do with the changes in voltage at the substation, because they don't really know what those voltages are on a continuous basis. They don't have the metering today out in the grid to watch that. Today, the utility uses capacitor banks for power quality, but what we want to do for CDR is to use capacitor banks, and we may have to add some capacitor banks, we may have to move some around for CDR, but what we want to do is to levelize the voltage down all of the paths of the feeder. And what I'm showing here is just an example. We're putting capacitor banks out on the grid to bring all of the voltages up to, say, 125 volts. And this is just an example. And you're thinking, well, we talked about lowering the voltage, why are we raising them? But what we need to do first is to make them level at some voltage, and then we can use that load tap changer to lower the voltage into a lower range. And this is really key, because if you don't levelize the voltages out in the grid, then you can't do a good job at the substation of telling the load tap changer to lower all of the voltages and still be in a safe range for all of the customers. So the load tap changer lowers all of the voltages at once, and now I'm showing that you now have a grid where all of the voltages are down in the lower levels, say at 117 volts, with some ability to survive a little power swings with loads changing. But then why stop there, or why not stop there? Traditionally, conservation voltage reduction was used in states like California back in the 70s. When they were having peak energy problems, they actually required their utilities to do an older form of CDR. But what they really did was they took statistics and went out and measured voltages, and then they kind of tried to just lower the voltage at the substation without knowing what was really happening out on the grid. So they had to do it cautiously. It didn't provide much savings, and it was done manually. So they had to send people to the substations regularly to change the voltages, and eventually that was pretty much abandoned. But there is a better way, and that's what I'm going to talk about now, which is to do this adaptively and dynamically with computers and a communication network. And the reason that this older technique, just a little bit more detail, didn't work is that voltages on every feeder change by the time of the day. Morning load is different than afternoon and evening. The day of the week, weekdays and weekends are quite different. The seasons, summer, winter, and spring and fall. So the loads change quite rapidly, sometimes regularly, depending on the weather and that sort of thing, but they're changing constantly. So we need a system that can adaptively react to what's actually happening. This requires us to really put voltage meters at strategic locations in the grid. XL Energy has done some pilots, and I'll show you a slide on that in a minute, but they found they really only needed 6 to 8 meters for each feeder. If you have AMI meters at customer locations, you can use those, but you don't have to have them. You can put standard meters on key locations within the grid, and you don't really need that many of them. You then need a communication system to get the readings back to the substation. Substations already communicate with central utility locations through the SCADA transmission system, but we need communications that work out in the grid itself. We also need then the software at a controller, and that could either be in a substation, it could be at a central location and talk to the substations, or pretty much at any location. So this CVR controller will adaptively adjust the capacitor banks on the substation feeders and the load tap changers for optimal energy savings. Now I'm going to answer the question, does CVR actually save energy? It's one thing to have a model and to talk about what it might do, but there are pilot projects. There have been a number of them across the country, and there also is a national study done by PNNL that shows that we can get significant energy savings for all customers if we do this voltage reduction in the right way. You can really run a CVR system in two modes. You can either run it to maximize the energy savings for the customer all the time, or you can run it in a capacity reduction mode, which will mostly look at peak load days and try to reduce the peak load that the utility is trying to generate electricity for. What most utilities are deciding on today is the energy savings mode. You get a little bit of capacity reduction as well, but if you can save 2% or even 3% on everyone's electricity use, you can reduce customer bills, reduce the fuel that's burned and therefore cost to the utility, and you do get a little bit of capacity reduction as well. If you run it in the capacity reduction mode, as I said, you're only really using the CVR for the peak load days. So you get a little more capacity savings, but you don't get the energy savings. There are additional benefits from CVR. You get some reduction in grid losses. Most of the savings in energy is behind the customer meter. So your refrigerator runs more efficiently, your air conditioner runs more efficiently and uses less energy. But there are also some savings in the grid itself. There are losses in the grid, and when you lower the voltage, it lowers the energy that's lost in the grid. But it's only about 5%. 95% of the savings are actually in the customer's homes. The other thing that the CVR is a building block for other grid improvements. You're putting a communication system out in the grid, you're putting metering out in the grid, and these are really building blocks for automated fault location, fault isolation, and increased reliability. There's also an advantage in integrating distributed generation. When the utility has metering out in the grid, they can see problems that start occurring when you have a lot of distributed generation. Maybe it's a bright day and the load is actually low because it's not hot, so you've got a lot of solar producing. You need to lower the grid voltage a little bit, and this system will allow that to happen in an automated way. And it also improves reactive power. Reactive power is a problem that is caused largely by motors because the current and the voltage gets out of phase. That's a complex subject, but someone once said it's like foam on a beer. Reactive power is like the foam on the beer. It doesn't really satisfy your thirst, but it's there, and it's something you need to reduce. So the CVR actually will improve reactive power on the grid. The utility, I'm sure, does a good job already today. The CVR will make it even a little better. Two examples in our region I wanted to talk to you about very quickly. Public Service of Colorado did 2 pilots a few years ago. They had very good success with it. So they are the first utility that I know of in the country that has proposed doing CVR on their entire system. So every feeder. They're proposing a $92 million project that would have a 5-year rollout. It would operate in the energy savings mode, and their projections are it would save 2% of all energy use by all of their customers. So this is an energy efficiency methodology that can benefit all customers. You don't have to do anything in your home to get this benefit. It will reduce your electricity bills. They also are projecting a 1% capacity savings for the system. So on peak days, you get 1% less generation needed. And the decision on to move forward with this project is pending at the PUC in Colorado. The big discussion on whether to do it or not was not whether or not it's a good idea. Everyone said it's a good idea. The question is, how much incentive does Xcel need in order to go ahead with this project? how much should they be compensated, and should they be rewarded for doing this very effectively? So what are the extra incentives beyond putting it in the rate base? And that's the real question. And we'll find out pretty soon how they will rule on this. I was in Nevada a couple of weeks ago speaking on this topic. The Public Utility Commission in Nevada is very interested in CDR. They have pushed NV Energy to conduct a large pilot, and that pilot has gotten approval. So NV Energy is in the process of selecting 6 substations and all associated feeders to run a year-long pilot of CDR. And I think that's very exciting. It's in the Las Vegas area. CDR does work a little better in urban areas than in rural areas, so they wanted to start with their more urban area for this pilot. And if it turns out well, as we expect, I'm sure they will consider putting it out system-wide. NARUC has also recommended CDR as a grid improvement that utility commissions and corporation commissions should consider. I provided, I believe you have the complete document, the NARUC document, where they talk about the benefits and then the fact that utilities need some support in funding these types of projects. So what would I recommend as the next steps for Arizona? I think that Arizona should consider a pilot project for CDR using at least 2 substations and all associated feeders. I think first you need to select the substations that would work well. They have a lot of engineering detail on all of their substations and associated feeders. And then I would encourage you to work with APS to look at a pilot for Arizona. And with that, I'd be very happy to answer questions.
Okay, very good. Very good presentation. I guess and I just want to understand for sure how this is working. Basically, the situation is there's an upfront cost to do this, and so you don't actually really realize the savings until a later point in time. And so see, you said Colorado, but was it Colorado was the one that has already done the pilot, right?
Yes, and I think I could answer your question. Public Service of Colorado is looking at a 5-year rollout, but they would start saving money for customers after 1 year. The rollout is when you're touching every feeder in the whole system, that takes a long time. But they would implement the control software, a basic communication system, and a number of feeders in the first year. So you actually see rolling benefit to all the customers at substations that have received the treatment pretty much immediately, within a year. The investment, the $92 million is divided up between additional capacitor banks, communication system, the software to run it, and just getting out and working on all of the feeders. So I could actually provide you with the breakdown that Excel has projected of those costs, just so you could see what they're projecting.
Okay, and they've already run a pilot and have been satisfied with the results of the pilot, so now they're going to go system-wide.
Yes.
In a 5-year rollout period. Okay. But they're still waiting a decision of the commission.
Yes, on how to fund it. Would it be rate-based? Would it be part of the demand-side management program in Colorado? Would they get performance incentives? So there were a number of incentives that Excel was asking for, and the commissioner will decide what's appropriate.
Okay. Do you have a feeling for what kind of a time frame they're looking at?
I believe I saw on an email that they're actually deliberating today. So
okay. So,
this is
so soon,
imminent.
possibly.
Yes.
Okay. All right. Any other questions? Yes. Yeah.
Thank you, Commissioner Burns. Just a quick question. You mentioned the need in that budget you were just referencing for a communications network that would go throughout the grid. Do you have an idea what kind of technology we're talking about? A microwave link? Are we talking about additional utilization of existing infrastructure?
It depends on what the utility already has in place. Many utilities can use existing infrastructure. If you had nothing today, you could go with some of the smart grid communication technologies, the modular, or you could use cell linkage. You don't need many meters, so that means the communication system isn't that expensive. It's not like a full smart grid at all.
Mr. Burns.
Thank you, Mr. Wilson. That was a very good presentation. I appreciate it. I was going to ask you about the cost, and then just as I was writing that question down, you came to it. So what I'm wondering is, you talk a lot about the customers' savings on their bills, which is something customers always like to hear. But I know some of our Arizona customers who've done energy savings or energy efficiency implemented various of the programs have been unhappy because they haven't achieved the savings that they wanted to achieve because then there was an increased cost somewhere else on something else. So obviously the investment would go into rate base, and you're talking about whether there'd be performance incentives and, actually whether there'd be any, what do you call it? We have an LFCR here, that kind of thing that would be affected. So this 2%, you have energy savings. I'm assuming that equates, you're saying this is the cost savings from not using that energy. Was that calculated after the $92 million? I mean, I know you said they haven't even decided what other incentives there might be to the utility, so I'm assuming that this was calculated prior to a return on investment.
It's actually a little bit of both. The business case for CVR, and I've reviewed several of them, the payback is about 3 years for that initial investment. And then now that depends on, as Commissioner Smith asked, on what the communication system already in place is. But it's about 3 years, which is pretty good. So 2% doesn't seem like a lot, and as you said, since these extra costs go into the rate base, and then if you reduce the amount of energy you're using, there is a rate adjustment. But there will be a real savings on the bill, because this is something that we do out in the grid, but it benefits the customer. So you don't need to constantly, modify your behavior or run a system in the house. It actually does work. Will you notice, 1 or 2% on your bill? No, but it would slow down the rate increases a little bit. So it's not like I can promise 10% and you'll see it. It's a small bit, but 2% reduction in fuel is a big deal. Really system-wide. That's a lot
if it's realized, and I understand, there's nobody really fully doing it, but I guess I get a little bit concerned about the promises that we make here and then the disappointment, and if we don't do it right and we make promises that don't end up coming to pass, then we sort of kill the whole desire for energy efficiency, and we don't want to do that. So I'll be real interested, and I really appreciate your presentation, and I'm not taking issue with it. I'm just thinking this through, and if Colorado, it'd be interesting to follow Colorado and see what they do and how it turns out.
And I just might add, that's one of the reasons it's important to do a pilot. I would definitely not say, let's go out and put this system-wide in APS territory. I think a pilot should be conducted and see what you actually get here with your load, because it's different than Colorado.
Yeah, I mean, it might be a good thing to do just for other reasons other than cost savings, even if it's a wash. I don't know, but just, yes, I think the pilot is clearly a good idea. In their pilot, did they discover a savings? Or
yes.
How can you even really do that correctly for a pilot? You can't have everything in place, so it's really hard to.
Well, they did the pilots by setting up the system at a substation and then controlling the feeders on that substation. And during the pilot, they would run the system for one day and then off a day. So on and off and on and off, and see, over time, what was the average savings. Now, that's not the way you would do it when you do the whole system, because you don't want it running only half the time. And the measurement and verification issue has been under debate. But the newer software systems that implement this help with that. But
Okay, and they did not have any voltage issues? Any low voltage, no complaints from customers? That wasn't a problem?
Right. There was no increase and even a decrease in many cases in complaints. So, yes.
Okay, thank you.
Okay, also, point of interest, it's my understanding now that APS has already done a CVR pilot, so we need to follow up on that. So. Okay, staff question. Yes, Steve.
You might be able to answer.
It's on.
You might be able to answer this, or maybe APS. But it seems like APS did propose something in the voltage VAR optimization in their last energy efficiency. And is this one of those items that is not currently allowed to be counted in our rules for their energy efficiency?
I'm really not familiar with your rules, so I couldn't answer that.
Yeah.
But many utilities have done small pilots. I'd have to look and see what they did to really be able to comment on how does it compare with what I'm proposing.
Any other questions, Steve?
No, unless APS could answer it, I don't know.
Yeah, I guess we would ask if APS would like to respond and sort of bring us up to date on the spot.